Hello and welcome to PCB Chat. I'm Mike Buteau, editor of Printed Circuit Design and Fabrication and Circuits Assembly. Our sponsor today is PCB West, the leading trade show for electronics design, fabrication, and assembly, coming this September to the Santa Clara Convention Center in California. Learn more at PCBWest.com. And I'd like to remind listeners that PCB Chat is now available on Spotify. So in addition to finding us at our website at PCBchat.com, listeners can also download our podcast at iTunes, Google Play, and now at Spotify. I'm honored to have two of the preeminent flex engineers in the industry with us on PCB Chat today. Mark Finstad is Senior Application Engineer for Flexible Circuit Technologies. He has over 30 years of experience designing and manufacturing flexible circuits for the commercial, medical, and military avionics applications. He co-chairs the IPC-2223 Design Standard for Flexible Printed Boards and co-authors the Ask the Flexperts column for PCD&amp. Also joining us is Nick Koop. Nick is a Senior Field Application Engineer for TTM Technologies and has over 30 years of design, manufacturing, and management experience in the flexible circuit industry. He developed and applied advanced PCB technologies to support a wide range of medical, military, and global security applications. Nick is Vice Chairman of the IPC Flexible Circuits Committee, Co-Chair for the IPC 6013 Qualification and Performance Specification for Flexible Printed Boards Subcommittee, and he also co-authors the Ask the Flexperts column for PCD&amp. And Mark and Nick will be speaking at PCB West next month. Welcome to PCB Chat, guys.
Thanks, Mike.
In your columns and during your presentations, you often return to the issue of material selection. How does the choice of polyamide or polyester compare with rigid material selection? Is the decision tree the same?
Nick, you want to take that one?
Sure, I can start. If I were to concentrate more on the aerospace and defense world, polyester-type materials are pretty rarely used. There's a big difference there between the polyesters and the polyamides, especially related to temperature. Polyesters have very low temperature capabilities, so typical soldering operations, that type of thing, are not readily done with a polyester. And you typically won't see more than a two-layer polyester circuit. So they're pretty rare. The polyamide right now dominates the market. There have been some others like LCP that have been trying to get in for other reasons, but haven't really got a ton of traction yet. Unlike the rigid world where we have an untold number of FR4s and then the polyamide glass, where we see a lot more of those choices going on. There are a bunch of different polyamide suppliers now that didn't used to be there. I think Mark's used a few more of those, and maybe talk a little bit about that. But we see polyamide as still the preeminent flex material that's getting used in the market today. I don't know, Mark, if you want to add a little more to that.
Yeah, I mean, really the only reason anybody would use polyester is price. It doesn't give you any performance improvements at all. If you're looking for something that is really, really cheap, then that's one thing that would push you towards polyester. And typically when you're using polyester, you're also using printed conductors. So where we see those most of the times in commercial applications, where you're going from some type of display down to a rigid PCB board. And so you'll have, the silver ring circuits and then a tail coming off with a zip connector that can make that connection very inexpensively. Just from a bigger standpoint on materials in general, I mean, the reasons we hit on them is because unlike rigid PCBs, we have to be concerned about both the electrical and mechanical and physical properties of the material and the finished circuit. And a lot of times, if you are trying to get something that really works well for you electrically, most of the properties that make a material good electrically are going to work against you mechanically. So it ends up being a balancing act. It doesn't do any good to have a flawless electrical circuit if you bend it and it breaks. So typically there's some give and take where you can get acceptable electrical performance, but also be able to do the bending and folding and mutilating that occurs when these things are installed, and be able to do that without failures.
Nick, you mentioned LCPs. What applications do you tend to see those being used in?
Well, the first one that it was originally looking at was on the medical side. There was some thought that there'd be some advantages there for LCP in terms of lower moisture absorption. That's kind of that material's claim to fame. So there have been some limited case where it's been used there. I think some folks have looked at LCPs maybe for a high-speed, low-loss type of situation. So in that situation, then it starts to have to compete with some of the other Teflon variants that we might use in a flex circuit as well. So it's been trying to get into the market for quite a long time. It does come at a cost premium. So unlike the polyesters, which are low cost, the LCPs and the Teflons tend to be higher cost, with the polyamide sitting kind of in the middle, which is why it seems to enjoy the biggest part of the market. And even on the high-speed side of the world, people are realizing that the polyamide flex material is better than almost every rigid material out there. It's like a 3 type decay, and the loss is down at about 0.003, so it's quite good. The acrylic adhesive is a weak link there, but there are some other things people are doing there to get around that. And that's where some of the material selections come in on occasion. If it's truly a high-speed situation, what might we do there? But yeah, the LCP is looking for its place in the world still a little bit. Like a lot of the other materials, even the Teflons are kind of niche materials right now. So polyamide is still the king right now in the circuit market.
Yeah, and one other sticking point on most of the high-speed flex materials, in addition to being higher cost, they are more difficult to process and almost always requires high-temp lamination. So you may limit the number of vendors that will even look at an application that you're using, the Teflons or the LCPs, because they're laminating up around 300 C, and most standard flex presses don't go anywhere near that in temperature. So you have to find someone that has both the equipment and the know-how to run with that, because LCPs are thermoplastics, so they reflow each time they hit temperature. It's not a thermal setting adhesive like acrylic or epoxy. So there are some processing stumbling blocks also that you'll have to deal with. And like I said, if your vendor base gets smaller, typically that is the price driver.
Both of you have centered on some of the two big drawbacks to using flex. Traditionally that's been cost and the processability. What has been changing of late to make flex a preferred solution?
Yeah, flex is always going to be more expensive than a comparable rigid PCB, but it's rare that anybody would ever make a decision to switch from rigid to flex just because. There usually has to be something else that drives that decision, whether you have a limited amount of space to work with, or you have weight constraints, or just the need to be able to form in 3 dimensions. And in reality, the vast majority of flex designs aren't driven by the want or need to change out a rigid PCB. Typically, you're trying to make an interconnect between displays or connectors or PCBs or something, and you don't have room for wires or harnesses, so you go with flex. But then flex gives you the added benefit to be able to incorporate circuitry and components and pick up some of that load also. So it's not really you're swapping out a rigid PCB for a flex. There's usually something that drives you to flex in the first place. And since you're there, then you might as well go ahead and try and pick up as much other stuff as you can also, such as like the SMT and the extra circuitry you can put on it.
Yeah, that's great, Mark. I think that's a good point. What we're seeing in a lot of cases, and exactly like Mark's talking about, is usually you don't replace a rigid board with a flex, but you may replace a rigid board in a harness and other things with a rigid flex, for example, or you might replace a wire harness with a flex. We find in a lot of those cases that we can create a better circuit that way, and where people start to save money. There might be a little bit more upfront costs in some cases, but they save a ton of money when it comes to reliability in the end, because we end up eliminating a lot of interconnections where there might have been a failure mode. So we can see in some cases 4 to 6x improvement in mean time between failure. So that can be a big driver in some of the cases. We also, in some cases, we're finding we can just replace a wire harness, and we get a lot more performance out of that. We eliminate a lot of skew and a lot better signal integrity than bundles of wire. So that's definitely a case for that. And as Mark mentioned in the 3D situation, there are some really, really creative designers out there, and you'll see a bunch of them again, I'm sure, at PCB West, who figured out how to take some of these boards and go, if I just do this, this, and this with a little origami, I can make a really neat total package here. And so they gain a lot of advantage in their finished package size and shape that offsets a lot of costs for them. From a processing standpoint, I think the industry's got a lot more mature. We pretty much understand exactly what we need to do to make a circuit work, what will work, what won't. How to scale these materials. Flex materials have to be scaled differently than rigid materials, and how to blend those two together. So that's helped quite a bit. I think it's been a learning thing over the years, and most of the folks have figured out how to put them together quite well. So we don't see huge differences in cost between the flex and like, say, a cable. And in a lot of cases, we find we can provide a better part overall.
Yeah, just building on what Nick said, when you go to rigid flex, you also can eliminate board-to-board connectors, and even if you were going to have looking at maybe putting a flex to link a couple of PCBs together, when you move to rigid flex, you don't have those discontinuities where you have to have board to flex connectors and then another flex to board connector on the other end. You can just characterize your traces so you get nice, smooth transitions between materials, and you get better signal performance overall. It does come at a cost. A rigid flex is going to cost more than comparable PCBs and flex, but there are times where there's the need for it, and if you're driven to that, you will get better performance out of it.
Nick, you mentioned the flex origami. I think Mark wrote a column about that some time ago.
Yeah, I think you're right. I think we've both seen over the years some just really creative folks come up with things that, in terms of how it's going to fit into a package, they take advantage of 3D. So if you can think in 3 dimensions of how this might all go together, that's great. And sometimes what's really helpful for us is, from the manufacturing side, is to see what that person's thinking, what it's going to look like in 3D. I literally have one on my screen right now, work with a customer, their 3D part. He's showing me what it's going to look like, and he's like, this is what it's going to look like. I don't have many options, but he actually has on the one end for one I/O connector, the end could come off of the very end of the part or the left side or the right side. He's still got some design freedom yet on that. And so we're looking at that and say, well, in this case, it looks like, well, if it comes right out of the very end of the part, I can get about 25% more parts on my manufacturing panel and save you roughly 25% on your unit pricing. So we're working back and forth with them on that. And so seeing some of those folks do that and how they come around and go, well, I can get around the part and my component like this, that's helpful from that perspective. It's also helpful for us to see them and go, oh, boy, the way you're bending that, I see concerns. So sometimes we can help them with the mechanical part that Mark was talking about before.
Yeah, and the good thing about the customer that you're referring to is they made the call and asked somebody who's been doing it for a while rather than just blundering into it, because if you try to just blunder into some of these without knowing how it's going to perform, you may end up way down the road, and then once you send it to the flex manufacturer, you're going to find that the price is just staggering because you've got features on it that just won't nest on a panel very well, or it just plain isn't going to fit into the enclosure or be able to function reliably.
Now, how would you characterize the current rate of innovation on the materials side? Are fabricators and designers having any trouble keeping up with all the new offerings from the material vendors?
Well, like Nick said earlier, Polyamide rules the market, and I would say that way over 90% of everything made worldwide is still done on Polyamide. The others are trying to break into the market, but the cost and some of the other issues are kind of pushing back on that. So And Polyamide's been around for a long time. And Nick and I, in a previous life, were looking for alternatives and found out that there just wasn't a lot of stuff that does all the stuff that Polyamide does. It really is a fantastic material to make flex circuits out of.
With the rise of Asian manufacturing as well, there's been a lot of pricing pressure on the material manufacturers. There are Asian folks that are kind of coming in with Me Too products, and they're getting evaluated by different companies, and so they have to look at that and say, what's the competitive landscape look like? So that's probably been one thing that's helped moderate material costing. Yields have gone up quite a bit, so that's helped. There are some other materials out there. We briefly mentioned, Teflon, much like the rigid world, where people looked at like Rogers Teflon materials and others for some of the high speed and RF and antenna type work. There have been some flexible Teflon type materials, either hybrids or pure, that have come out. They're very interesting, and they provide some definite dielectric advantages. They also provide some manufacturing challenges. As you can imagine, Teflon is very soft and very pliable, and so it's much more difficult to handle that material and to make multiple layer circuits with it because things move around a lot. So that's been a challenge on that side of it. We talked about LCP and some of the advantages that might have. There are also some higher temp materials where some folks are looking at, hey, can I make essentially an all polyamide circuit? So that can be done, and we do some of that. Like Mark mentioned earlier, only certain people have the equipment to do that because it requires really high temperatures and pressures, and it's a niche. So, but there are some applications that really need high temperature or a resistance to higher work environment temperatures. So we see some of that. I think the next big push is probably going to be on the high-speed side. And as the communications and stuff go to the 5G, we'll see more things there. That how we're going to make a circuit that's going to handle the high frequencies.
Now, your flex presentations are heavy on real-world problems. Could you give me a flex horror story you've either personally experienced or has been shared with you, and what your solution or recommendation for it would be?
Just one? Just one? How much time do we have?
Well, for your PCB West presentation, you have 2 hours.
Yeah.
So we got a lot more time if people want to hear horror stories. I actually did an article for Printed Circuit Design and Fab a few years ago that was the don'ts of flexible circuit design. And the way I started out is I said, when you have a successful flex circuit design, you usually forget about it fairly quickly. But when you have a crash and burn, that's kind of burned in your memory, and you never forget it. And over the course of 35 plus years now, I tell my customers and my students, I can't tell you everything that'll work, but I can tell you pretty much everything that won't work. So if you rule out all the stuff that doesn't work, you usually end up with something that will work for you. But one that's fairly recent is and it's kind of near and dear to my heart because I know a lot of people are struggling with it, is the new ZIF connectors the dual row ZIF connectors they have for connecting flex to hardboards. If you look at the design of these, the old style ZIF connectors that just had the straight through connectors or straight through traces, you were looking for an overall thickness of about 12 thousandths of an inch nominal, plus or minus 1. And so it's fairly rigid, and would hold up really pretty well, pretty good sized conductors going through there. And those have been used for years and years and years successfully. Unfortunately, you are limited in connectivity because you can only get so many conductors into that area. So a lot of connector manufacturers came out with the dual row ZIF connectors where you have 2 rows of contact pads, and you end up with a 4 mil wide trace that snakes between the inboard traces or inboard pads to get to the outboard pads. And that entire area ends up getting gold and nickel plated, so it's very, very fragile. Nickel is brittle, and if you bend it really any at all, you can get cracks in your conductors. And then the specifications for these are looking for a nominal thickness in that area of 8 mils as opposed to 12 mils. I'm not really sure why they went that direction with it, but that makes it very easy to bend, actually. And so what happens is when you put these ZIF connectors into the flex into the ZIF connector, if you put it in there absolutely perfectly and you clamp it down, you have no problem at all. But there's almost no room for any variability at all. If it goes in there at even the slightest angle, or it's in too deep or too shallow, or anything that causes it to bend, when you clamp it down, you end up getting either full fractures or just micro cracks that end up propagating. And I brought this up at one of the last 2223 meetings at the end, just to see if I was the only one that had been hearing all these horror stories, and every hand in the room went up and saying, yeah, we thought it was just us, and here everybody is struggling with it. So it's something that we're actually putting it into 2223. It'll be in the next release where there'll be a caution note on using those. We're not saying don't use them. We're just saying if you do, you better really have control of your installation process. Because if you start doing, if you're only doing 100 pieces, it's very easy to plug them in perfectly. But if you're doing tens of thousands or hundreds of thousands or millions, it's just human nature that people are going to be careless, and they're going to start moving too quickly, and things are going to get installed improperly, and most of the time the operator doesn't even know that they damaged it when they clamp it down. So that's my horror story, is that I've just seen a lot of customers that have been struggling with this, and they don't realize it until they're in full-blown production, and it's like too late to change and go back. They're stuck with it, and so that's what's going on now.
That's a great example of also the value of being involved in the IPC and going to things like PCB West and getting to talk to other designers and that kind of thing and see who's, what people are doing, what's working and what's not, because you find out that the struggles you're having are probably very similar to somebody else's most of the time. I can think of one as well, a little different situation actually, where we started building a part, and I always like saying this, it's just a simple 4-layer flex, nothing fancy, as everybody would say, the easy parts, which always end up being the ones that are the problem. Well, sure enough, we started building it, and we are struggling. Our yields are 50 to 55% overall by the time we get out the door. We're having opens and shorts and a number of different issues, and so I got asked to look at this part. And the factory's about ready to throw up their hands and say, we give up. We're not going to build this again anymore. And in fact, they actually raised the price of the customer. They had doubled it. The customer's still buying it, but even at double the price, we couldn't deliver because we couldn't, get a consistent yield. Well, it turns out this part, as a 4-layer part, had, traces on all 4 layers. The outer layers were getting plated, and there were traces between pads, very tight pad patterns, and nothing was centered, and lots of little issues in there. So long story short, we looked at that and said, hey, how could we fix this? We actually told the customer we had a solution and that we would redesign the part for them, which we did. And we went from a 4-layer up to a 6-layer part. And some people say, hey, don't add layers. That always makes it more expensive and more complex. Well, actually it didn't in this case. The outer 2 layers, we turned them into mostly pad layers. It allowed us to reroute all the traces on internal non-plated layers, which always helps. We also found that in the original design that however the parts got routed, a typical auto router, the person set a minimum spacing. And so when that happens, as it routes traces between pads, it almost always does not center them. It puts them off to the side, and it'll meet the minimum spacing on one side. Well, we had 3 mil spacing on one side and 7 mils on the other. So we centered everything back up, rearranged all those traces, and it brought stuff up onto the outer layers just at the connector patterns. That worked really well. We ended up overall in the area of the part that flexes, we ended up with the exact same thickness. In the rigid areas, it was pretty much the same because we swapped out some covers for some substrates. And so in the end, the customer really couldn't tell the difference functionally and certainly mechanically, but our etch yields went much higher. We took a part that was about a 55% yield up to about a 90% yield on the first pass. So it was a quick one where we were able to go back in this case, luckily be able to go in and redesign the part, at least on all the internal factors, and turn it into actually a manufacturable part for that customer. And actually, we're still building that part today.
And that is, I think, a big misconception that a lot of customers think that, if they can pack it all onto 3 layers or 4 layers by making the features ultra tiny and the pads ultra tiny and starting to go with blind and buried vias, that they're going to save money. It's a balancing act there, too. A very simple 6-layer that you're doing at 90% is going to be a heck of a lot less expensive than a 4-layer where you're really struggling and only getting 50% yield. So that's why it's so important to be asking those questions of people that build these things for a living, and get those answers early in the design process, because if you wait till the end, then it's too late. So pretty much any reputable manufacturer is more than willing to take a quick look at your design and steer you down that direction, because if you are going down the wrong path, it doesn't do anybody any good, because it's all going to have to be ripped up and redone, at a later time.
So that's a great point about the trade-offs and the need to communicate between the designer and the fabricator. And I know you'll be presenting much, much more about this during your session at PCB West, titled Ask the Flexperts, Flexible Circuit Design Through Test with Lessons Learned. What can attendees expect to get from that course?
Hopefully we can share a lot of the things that we found don't work, like I talked about earlier. And because we've been doing this for so long, we hear a lot of the questions that come in from designers. And so we've tried to kind of tailor our course around the types of things people ask. And a lot of them are the mechanical performance. How do you know if you can bend and fold something? I know that one of Nick's modules is, when's it a good time to use a flex? Where should I put it? Why would I want to use a flex in any given application? Cost drivers is always an important one. Just overall mechanical layout of the flex. There's just lots of things we've learned over the years, and we try to cover as much of that as we can.
Yeah, I think we cover a lot too on materials and those different trade-offs and mechanicals, as well as some of the electrical part of it. And usually we get a pretty good audience. We get some people that start throwing questions at us, and that's when it gets to be the most interesting, because they usually are throwing real-life situations they're struggling with, and we talk about how that could be solved. And or some of those folks end up saying, hey, well, I had one like that too, and here's how I did it. So sometimes, so to speak, we lose control of it and let another expert in the room help out as well. So, however we get the information out is the best.
Yeah, one of the things we tell our students at the very beginning is, if you have a question, don't wait until we get to a break to ask. If you got a question, raise your hand. We'd much rather address what's important to you right away. The other thing is, at the end of the day, there's only going to be 2 people walking out of that room, flex experts, and that's Nick and I. So we don't expect you're going to become a flex expert in the 2 hours that we have you captive there, but we're going to give you 2 very important tools, and that's our business cards, where we have our phone number on it. So you can call us, and you can get our feedback on any designs that you have, and hopefully get you on the right path.
Great. Well, that's about all the time we have for today. My guests today have been Mark Finstad of Flexible Circuit Technologies and Nick Koop of TTM Technologies. Listeners who want to learn more about flex circuit design and manufacturing are encouraged to come listen to Mark and Nick on Thursday, September 13th from 9 to 11 a.m. at the Santa Clara Convention Center during PCB West. This has been PCB Chat with Mike Butow. Have a nice day.